Okay, so today we are going to discuss another type of sensor, which is magnetoelectric sensor. So as the name implies, so this sensor basically is used to detect magnetic field. Yeah, magnetic field. Of course, we have discussed about inductive sensor, which is also related to electromagnetic field, but this is especially when with inductive, you are still also dealing with electric field, yeah, not necessarily magnetic field. So in magnetoelectric sensor, it uses physical phenomena that convert the parameters that you want to measure using magnetoelectric effect. Okay, so here, and it is not specifically used for detecting magnetic field only. It could use velocity, displacement, acceleration, and as well as other measuring quantities, including the Earth magnetic field, for example. And the magnetoelectric sensors can be divided into two types of sensor. First one is magnetoelectric induction sensors. They are related still with inductive based sensor, but the other one is Hall sensor. Hall sensor is using different type of mechanism to detect magnetic field. So, and this one, they are used quite widely also in biomedical field, especially like in MRI, magnetic resonance imaging. The use of magnetoelectric sensor is quite prevalent. It's used a lot, as well as other sensors which require the use of magnetic field. For example, um, there is an electrocardiograph. There is also magnetocardiograph. Yeah, magnetocardiograph, I think the group of Ezra and Andy at that time presented about magnetocardiograph MCG. So in that case, then magnetoelectric sensor is used to convert the changes of magnetic field into electricity. And let's first discuss the first type of magnetoelectric sensor, which is magnetoelectric induction sensor. And this is used according to the Faraday's law of electromagnetic induction, where a conductor is moving. When a conductor is moving, you have a conductor means a wire that has even just a wire, a conductor, moving in a stable magnetic field perpendicularly to the magnetic field direction, then it will induce electromagnetic force, electromotive force. Yeah, so then voltage will be created along the conductor, which means that then current will flow. So there's that electromotive force E is can be calculated from the change in the flux in a magnetic flux using this formula E equals d phi dt, and the magnetic flux itself comes from the magnetic field d times the length, magnetic induction intensity of the magnetic field, the length of the conductor L, and x here is the change, the change of relative velocity. The x dt is the relative velocity of the conductor in that stable magnetic field. So the conductor is moving inside that magnetic field with a velocity of dx dt or v. Okay, so it is then proportional to that velocity as well as proportional to the magnetic field here, and also proportional to the effective length of that conductor. If then the electromagnetic field has omega circles, omega number of circles, the induced electromagnetic force of that induction coil, because it is caused by a coil instead of a single conductor, then the electromotive force can be calculated using this Faraday formula also, the modification of the previous Faraday formula, that E equals to negative omega d psi dt. Yeah, so here there are two different modes, different types of magnetoelectric induction sensor, either the variable magnetic flux mode or the magnetic flux mode is constant. The magnetic flux is constant. So these two modes of operations can be used. Either the magnetic flux is changing, according to this figure 3.38 here. Here in this case, the magnetic flux is changing, but the conductor doesn't change. Here is open magnetic circuit, then or a constant magnetic flux. In this one, the magnetic flux is provided by this permanent magnet, and it is the conductor that is moving in that magnetic flux. Similarly here, there are permanent magnets, and this is constant. The magnetic flux is constant, but then the conductor moves relatively towards that magnetic field. In this case, actually, it is the iron that is moving. It is the permanent magnet, the iron that is moving due to velocity or acceleration, and as a result, the magnetic flux that impinges on the coil will change, but the magnetic flux itself is constant. In this case, the conductor is the one that is moving, the moving coil. The coil is the one that moving here relative to the magnetic field. And with this case, this is a magnetoelectric induction sensor with the flux is changing. The magnetic flux is changing. This is, for example, due to a rotational metal near the coil. This is the induced coil as well as the magnetic field. And in this case, we have also, this is a shaft, I think, a shaft moving inside a magnetic flux. The induced electromotive force of when the magnetic flux is constant, then we calculate using this formula. Basically, this is similar to the previous formula. E equals to minus B0. B0 is the magnetic induction intensity in the working air gap. L is the average length of the coil. W is the number of the coil, the wounding number of the winding of the coil in the working air gap. V is the velocity, relative velocity. So either the coil is the one that is moving, or the magnetic core itself, the magnetic iron itself, is the one that is moving, right? Exemplified by these two figures. Okay. So here, for example, if we see here, this is the model of magnetoelectric induction sensor, where it is modeled as an electromotive source. It's an voltage source, voltage source, having a series resistance, which is connected then to the resistance of the RF here, the input resistance. Then, as we can calculate using circuit analysis, the current flowing I0, I output will be equals to the E divided by R plus RF. RF is the input resistance. R is the equivalent resistance of the coils. And E is replaced or substituted using the Faraday's law, having constant constant magnetic field, magnetic flux. So equals to B0 LW divided by R plus RF. Then is the current sensitivity of the sensor is the change of the current output is a function of the velocity. If we want to use this, for example, to detect displacement of velocity, then S equals to I0 divided by V. So then we have this B0 LW divided by R plus RF. When the working temperature varies or under external magnetic fields disturbing and mechanical vibrating, the sensitivity will change also, and this is the relative error. So this is due for what we can say as a drift or sensitivity change due to the external magnetic field change, or for example, mechanical disturbance, mechanical vibration at L here. Yeah, so then the relative error gamma is defined as ds over s, yeah, which is equal here we db divided by b plus dl over l minus dr over r, because r here is in the denominator in the SI formula. When temperature changes, this tree will change also. Yeah, the length will expand. The R resistance usually will change also because it usually has temperature coefficient, which could be positive temperature coefficient or negative temperature coefficient, like a thermistor. The magnetic flux will also change because the permittivity will change. Therefore, each of these terms will be non-zero values. And temperature compensation is necessary to compensate this error due to the temperature changes using a thermomagnetic splitter. Okay, so this figure shows how the magnetic effect to the sensor current. So basically, symbol showing the Faraday law. Then the induction sensor will cause also the output of the induced electromotive force there with high sensitivity, and therefore do not require any gain amplifier at the output because it is already a voltage. So it could be used as a speed sensor, and integral or differential circuit can be used to get location, for example, or with differential we can get acceleration. Yeah, displacement or acceleration can be used. So then we can have this kind of circuit, yeah, either using differential or integral circuit. If you use differential, the differentiation of velocity over time, then we will obtain acceleration. If you use integral circuit, then we will obtain the displacement, yeah, the total displacement. Then after that, this can be amplified further and display and record. This is the block diagram of measuring circuit for magnetoelectric induction sensor. So you could implement this differential circuit, for example, and integral circuit also using op-amp and capacitive circuit. Okay, what is the application of magnetoelectric induction sensor, yeah, or the magnetic sensor? So it can be used to measure magnetic blood flow, for example. As we see that the blood itself, the hemoglobin binds to iron. Yeah, so it contains basically and charge also. Then it contains uh, some electrical charge, yeah, basically like a current. Then when a conductor moves in a magnetic field, while cutting that magnetic field lines, it will generate induced electromotive force, yeah, as shown here. Okay, so we have the conductive liquids. We can put two electrodes, then the uniform magnetic field flow through that inactive fluid. Or here, this is the cross-section diagram, and the principle is shown here. This is like the flow of blood inside that blood vessel, and you put a core here to induce the magnetic field. Yeah, parallel uniform magnetic field. Then the generated electromotive force can be calculated here as V equals to 2 times A times B times V. Yeah. A here I think is the diameter or something, the cross-sectional area. Yeah, the uniform, where B is the magnetic flux in gigasiemens. Flux density, V is the velocity, then the type this can be used to calculate the volume flow rate, Q, yeah. And so this equals to, the volume here equals to 2 times Q times B divided by pi times by A. Then the advantage of using this is that it has nothing to do the EMF that happens. It doesn't have. It has nothing to do with related with the blood flow distribution. And then the EMF will only relates to the instantaneous volume flow rate. Okay, that is how magnetic induction, magnetoelectric induction sensor is used. One of the application to measure blood flow. Let's go to the second type of magnetic sensor, which is based on Hall effect. And this is a different kind of magnetic sensor. Not based, the previous one is based on Faraday's law, maybe has similar principle like inductance-based sensor. Well, this one, Hall magnetic effect, is a little bit different or completely different because this is based on a different physical phenomena called as the Hall effect, which relates the magnetic and electric, magneticity and electricity, discovered in 1879. So this is the representation of a Hall device. Yeah, when we have a conductor, for example, yeah, like this, and it is placed in a magnetic field. So when a magnet was placed, its field was perpendicular to one face of a tin. Yeah, remember this one, the keyword here, it has to be a thin rectangle of gold, so a conductor through which current is flowing. So a difference of potential will occur at the opposite edges, yeah, of that thin conductor. At the opposite edges of this, here between this edge and the other edge here. Okay. He found that this voltage was proportional, so this is called as this VH. Yeah? This H was proportional to the current flowing through the conductor. And the flux density or magnetic induction perpendicular to the conductor. So again, the voltage here, the VH, the Hall voltage here, is proportional to the flux density B, yeah, the flux density, and also to the magnetic induction perpendicular to the conductor, shown here. Yeah, so for example, this is the external structural schematic diagram. So one here is the exciting electrode where current flows, and we have 2 and 2 dash here is at the edge, the Hall electrode where voltage is being measured. Yeah. And perpendicular electric field is piercing, yeah, or penetrating through this thin conductive electrode. So for a simple matter where there is only one type of charge carrier, in this case electrons, the Hall voltage UH will be given by this formula. UH equals the B times the I divided by NED. The B here is the magnetic flux, the I is the current flowing through the length of the thin conductor. Yeah. And E is the electromotive phenomenon. E, I think the thickness, yeah. The NED. Why there is no? N is, I think, the number of electron. E is the charge of electron. So the Hall coefficient is defined as RH equals to 1 over NE. So here 1 over NE is replaced by the symbol RH. The Hall coefficient times BI divided by D. D, I think, is the thickness. The thickness here of the plate. Okay, D is the thickness. So then the RH divided by D becomes this Hall constant, KH times current times B. So the voltage, the Hall voltage is proportional to the current flowing through the thin conductor and also proportional to the magnetic flux B. Yeah. So KH equals to RH divided by D is defined as the sensitivity of that Hall device. So from this equation, then the Hall voltage is in direct proportion to the excitation and magnetic field intensity, the excitation current here, and the magnetic field intensity. And the sensitivity here is indirect proportional to the Hall coefficient RH, yeah, which is basically equals to 1 over NE. And the inversely proportional to the thickness of the Hall. So you could increase the sensitivity by decreasing the thickness. The thinner the Hall device, then the more sensitive the Hall sensors towards magnetic field. Yeah, that's why it is usually to improve sensitivity, it is usually made into thin slices. The resistance between the excitation electrodes, between the two ends of the along the length of the conductor, is defined as R equals to the rho resistivity times the L divided by the cross-sectional area. Cross-sectional area is D, the thickness, times the B. B is the width, yeah, the width of the conductor. So R here equals to, while resistance is also equals to the voltage divided by the current, or the electromotive force multiplied by length divided by current, equals to replacing E here with V divided by mu N E V D, yeah, because mu mobility, yeah, equals to the voltage divided by E. Okay. So where mu is electromobility, so then the resistance equals rho LVD equals to L divided by this one, mu NE VD, and the sensitivity equals to 1 over NE, or equals the resistivity times the mobility of the electron. The resistivity times the electron mobility. So based on this, usually only semiconductor are suitable for manufacturing Hall device, because here the semiconductor has better RH coefficient, Hall coefficient, because it has better higher rho, higher resistivity, yeah, and mu as well as quite high electron mobility. With a normal conductor, then the resistivity is usually small. The copper, for example, or aluminum, the resistivity is small. While for semiconductor like silicon, p-doped silicon, and doped silicon, this rho can be tuned. The mobility can also be tuned. Okay, the structure is as shown here. Yeah, it is figure. 1 and 1 dash are connected to an electrode with exciting current or voltage. Is the exciting current here, 1 and 1. So at the at the two ends of the long conductor, and then the voltage is probed at the edge of that long conductor. The whole output down at the whole electrode. So this is actually the Hall element is the basic magnetic field sensor. It can measure the magnetic field. And usually the compass that you have in your smartphone is based on this Hall effect, made from a semiconductor thin film material. The signal conditioning needed then therefore will be an amplifier stage as well as temperature composition, because when temperature change, usually then the resistivity as well as mobility of the electron at the semiconductor will change also. Voltage regulation is needed when operating from an unregulated power supply. So this 3445 basic Hall effect sensor. So the Hall element is here, as you can see here. This is the exciting electrode, yeah, where voltage is being put, and then so that current flows from the two ends of the Hall effect. Then at the edge, the voltage, the electromotive force, the generated electromotive force is being detected, and amplified using a differential amplifier. So this can be implemented using standard bipolar transistor technology. So that's why it can be easily integrated into IC, and therefore it is widely used in the smartphone compared to if you use electromotive induction sensor. Yeah. If you use electromotive induction sensor, you require a lot of big structure. So when the Hall element of the excitation current is zero, yeah, then the location of the magnetic flux component is zero. Yeah, because then the Hall electric potential should also be zero since the current is not there. So no electric field, no magnetic field can be detected. So however, this value is usually not zero. There should be some leakage current. This is what we call as the measured electric potential is called as the allelic potential. And this is due to Hall electrons asymmetry, non-uniform resistivity of semiconductor material, which will cause non-uniform resistance, poor contact of the incentive electrodes, yeah, unevenness causing unevenness of the electrode current. And this is the formula of the allelic resistance. Okay. And when temperature changes, also the Hall potential usually will also change. And that's for this it is called as temperature coefficient for the Hall voltage. And this is an important effect, yeah, which we need to take into account because the surrounding temperature will always change, and this has to be taken into account. So, in order that we can still have accurate measurement of the magnetic flux, and this is where we use a bridge, similar like Whetstone bridge, used to compensate when there is unequal electrical potential. In this situation, A and B should be of the same equipotential surface, where we measure, but then in so A, the Hall electrode at the beginning should be zero, yeah, no electric, no magnetic field. And first we have to balance it, similar like in Whetstone bridge, right? So in that case, we can use this excitation electrode, and we can tune using this bridge the resistor, one of the resistors, such that then to nullify first the potential between A and B at the initial condition, yeah, to reduce the offset. As we have mentioned earlier, that temperature is important. Yeah, temperature can cause error, and because the Hall device usually will have temperature coefficient of the Hall effect. So here KH0 is the coefficient, the change under temperature T, yeah, under certain temperature T, and delta T is the change of temperature, and we have alpha as the temperature coefficient of the Hall voltage. Yeah, this will change the K, yeah, the coefficient, the sensitivity of the Hall effect. So to compensate for the change of this sensitivity due to the temperature coefficient of the Hall voltage alpha, then we can have this temperature coefficient temperature compensating circuit, having a current source, then some of the current is flown into a parallel, a shunt resistor to next to the Hall effect. Okay. Yeah. So if the initial temperature is T0, the input resistance is Ri0, sensitive coefficient is Kh. The shunt resistance is Rp0. When temperature increase to T0, the parameter of the circuit will be that the Ri here becomes Ri0 multiplied by 1 plus delta times delta T. Delta here is the temperature coefficient. Then Rp will need to be adjusted as well, so that Rp0 equals to 1 plus delta T. So delta is the temperature coefficient of the input resistance, beta is temperature coefficient of the shunt resistance. The IH, the current here flowing, this IH, you can calculate using current diffusion formula, RP divided by RP plus RI multiplied by the current source. And by arranging the equations above, we will have RP0, the shunt parallel resistor, equals to delta minus beta minus alpha times the RI0 divided by alpha. So the input resistance RI0, temperature coefficient, this delta is known, temperature coefficient of Hall voltage are set value. We can calculate the shunt resistance RP0 as well as the temperature coefficient beta. How are the Hall sensors applied in biomedical for biomedical field? Yeah, there is what we call as the whisker Hall sensor. Yeah, this is the whisker Hall sensor, and very small the Hall effect device. Since it produces very low signal level, usually it will require amplification. Yeah, so then after the amplification, it can be converted easily using ADC to the microprocessor. This, for example, then can be used in a flow sensor, Hall effect respiration flow sensor, by a magnet or by shunting the magnetic field, yeah, to measure the quantity of water or air flowing through that. So we have here the Hall sensor. We have the magnet field here at the perimeter, yeah, of the flow vessel. First, the flow rate is converted to the rotation speed of the blade here. Then this blade that contains this magnetic field will turn, right? Then this will, the turning here, which will cause magnetic flux changes, can be detected by the Hall sensor attached to the packaging here. Yeah, the Hall sensor will convert the rotation speed, the RPM, to pulse signal. Okay, are there any questions related to the Hall effect sensor, as well as magnetoelectric induction sensor? And this the Hall effect sensor, yeah, can be used in, I think, MRI sensor, yeah, or magnetocardiograph sensor, yeah, the Hall effect sensor, as well as the magnetoelectric induction sensor. Now, this one are some of the application, but it can also be used to detect other magnetic fields caused by the flow of our blood, for example. Okay, if no questions, then we will